All right, so we finished our discussion of the divergence. Now we want to finish our discussion of the divergence and curl, just with a couple of miscellaneous applications that you can see what we use it for. Obviously, this will not be the end of our discussion of divergence and curl. We will see it pop up in the next half of this unit, but it's just important to round this out, give you a couple of practical applications, and give some applications to stuff we've already covered. So let's get started and discuss the applications of the divergence and the curl. The first one is the extension of Green's theorem. Now, if we have a vector function or vector field, if you have a vector field f that is modeled by both some function of q and some function of r, so if we have q and r, well, then that means that what we are going to get is we will have a two-dimensional vector field. So we can model that in basis vector form. We say that f is equal to p times x basis vector plus q times the y basis vector. And if I want to take the curl of this guy, well, what we're going to get is we're only going to get the z component because we only have terms of x and y, and if we had a term of if we have a term of 0 in the z, then that means that any multiplications between the for the x basis vector and the y basis vector, the cross product will be 0. So our only non-zero component will be e sub z. So what we end up getting is we if I want to take the gradient or the curl of our vector field, I will end up getting the x derivative of q minus the y derivative of p, and that's multiplied by the e sub z basis vector. Now, if I actually dot product this with the e sub z basis vector, then the e sub z times e sub z goes to 1. So the final result there is partial q over partial x minus partial p over partial y. Now, this looks strangely familiar because this is the form of Green's theorem that we had inside of the double integral region. So what this means is we can actually try to write Green's theorem in vector form as opposed to in kind of that weird form where we had the pdx plus q dy. So what we'll do here is we will reformulate it such that the line integral over the boundary of some domain, so it's closed, of f dot dr is equal to the integral that we saw earlier, pdx plus q dy, which can be rewritten as the kind of volume generated when we take the curl of f and dot it with the z basis vector. And then that's with respect to some differential area, which I forgot to write. So that's with d squared x, right? So anyways, that's how we can reformulate Green's theorem. It's somewhat helpful to know. This is not the only time we will be seeing this formula in the future. Now, another application that we have is the Maxwell equations. Now, the Maxwell equations are the four fundamental equations in electromagnetism. They govern electromagnetic waves. They are differential equations that model waves. And we are going to look at them and then play around with them a little bit with what we know about the divergence and the curl. Now, here we go. So let's say that these are the four Maxwell's equations, which they are. These are in relativistic form. We have the divergence of the electric field is equal to 0. This isn't always true, so this is in a static space where there's no charge. If there was a charge, the divergence of the electric field would be non-zero. The divergence of the magnetic field is always 0 because there cannot be any magnetic monopoles. So since there are magnetic dipoles, that means everything that goes in must go out, such that there is a net zero divergence in the magnetic field. Both of these first equations are called the Gauss's laws. So we have Gauss's law for electricity, and then we have Gauss's law for magnetism. Now, it turns out actually that there's a Gauss's law for gravity as well. There's the Gauss's law that we're actually going to be talking about later on, which is in integral form, and that will be very helpful for us. It's also called the fundamental theorem for divergences. Anyways, we have the Gauss laws. Now we also have the Faraday law. The Faraday law says that the curl of the electric field is equal to -1/c, which is the speed of light, times the partial derivative of the magnetic field with respect to time. Okay? So then finally we have the Maxwell Ampere law. So this is Maxwell's correction to Ampere's law, which says that the curl of the magnetic field is equal to 1 over the speed of light times the derivative of the electric field with respect to time. So those are the four Maxwell's equations. They're very fundamental. Note that there's a differential form of the Maxwell equation, and there's also an integral form. We'll talk about the integral form towards the end of the series, but we'll look at the differential form for now. Anyways, if I want to kind of reformulate the one of these laws, if I want to, let's say I want to take the curl of the electric field, well then how can I model that by using the Maxwell equations that I know and some properties of the curl and the divergence. So what we have is the gradient, or the curl of E. Well, we have an equation for the curl of E. We have the Faraday law, the third equation. So we're going to use the third equation. We're going to substitute that in for nabla times E. So then we get the curl of -1 over c times the derivative of the magnetic field with respect to time. So what we can do is we can pull the speed of light out of the equation because it's a constant. So we get -1 over c times the curl of the derivative of the magnetic field with respect to time. Now, because let's expect that we can pull the time derivative out and then take the derivative of the curl itself. So we can pull the derivative out, the time derivative, so we get -1 over c times the derivative with respect to time of the curl of the magnetic field. Now finally, we've got the Maxwell Ampere law, the fourth equation, where you can substitute 1 over c dE dt in for the curl of B. So when we do that, what we get is we get -1 over c squared, because we get another 1 over c factor. And then we're taking the time derivative of the electric field, which is, of course, the second time derivative of the electric field. So thus we found that the curl of the electric field is equal to -1 over c squared times the second derivative of the electric field with respect to time. This is kind of how we can play around with divergence and curl a little bit. It's very helpful. So that kind of rounds off our discussion of the vector derivatives that we've covered earlier. In the next video, what I would like to do is talk about parametric surfaces. So that's kind of a prerequisite to what we're going to be covering. Then our next kind of big topic is going to be the idea of surface integrals. So we talked about line integrals, and we've talked about how we can think about them as densities. And now we're going to extend that one dimension, talk about surface integrals, or volume integrals too. So we'll talk about surface integrals, but to do that, we need to discuss surfaces in general. We haven't discussed how to parameterize surfaces just yet, so we're going to discuss surface parameterizations. Then we're just going to determine how to find the surface area of two-dimensional functions. So that's going to be like a generalization of arc length. Then we're actually going to think about finding like flow across surfaces. So for that, you need the area, surface area through an integral, and then you also need to find kind of like the flow through that. So one of the big things that we're going to be talking about is how to represent areas as vectors. So we will talk about that later. That's all to come. Very exciting stuff. We will see you in the next one. Thanks.